Alright, we'll talk about the part 2 of day 9 of Advent of Code. I will assume you've read the problem statement and you sort of came up with a brute force solution. The most sort of naive way of doing it would be to iterate through all the files from the end, and for each of those files you would iterate over the empty spaces, right? And so you have around n over 2 files and n over 2 empty spaces. So in the worst case, if for each file you have a lot of trouble to find an empty space that is compatible, then it would be a big of n squared algorithm, right? This works for the inputs they give you because the inputs are random, so they don't actually give you worst case scenarios. But I've put a test case that would take way too much time on this if you use a brute force solution. So feel free to try a solution. If it is an n square solution, it might fail. And by fail, I don't mean output the wrong result. I just mean or just take forever. So the idea here is we'll try and build a nlogn solution together. And the idea for such a sort of fast solution is when we have, let's say, a group of 4 blocks, we want to remember which is the smallest index such that there is 4 free spaces in a row, right? And here there's no such free space. And you could think could be fairly easy, right? When we build this list of empty spaces, we could remember for each of the width from 0 to 9 included, the list increasing order of the free spaces. The only problem is those lists won't be static, right? Because if we look at this, when I put those 2, 4 here, I use one of the spaces that had 3 empty spaces, which is good. I know which one is the smallest, but I'm creating a new one with 1 free space, and I should add this in the list of free spaces of size 1, and I would have to resort this list because I can't add it in the beginning or at the end or in the middle. I would need to resort it because I don't know exactly where to put it. And even inserting in the middle, even if I knew inserting in the middle of an array is still big of n, right? So that's the main problem. We want to remember where the smallest index for each width is, right? But we want also to be able to update those lists of free spaces for a given width in a fast time as well, in a time that is faster than big of n. And the idea here is to use a heap, right? Because with a heap, we'll be able to pop in big O of log n and pop them to a min heap. And we can push, so add in also log n, right? It'll be clearer when I maybe draw out the solution. I'll keep explaining on the example. Here we'll have 10 heaps, right? We'll have 1 heap for width of 0, which will always be empty. 1 heap for width of size 1. So initially it will be this element, this element, this element, this index, and this index, right? And whenever we pop width 1, we'll get the smallest index such that there's 1 space left, right? And we'll have 2. Here we don't have anything, and we'll have 3. And for 3, we have those 3 free spaces, and whenever we pop, we'll get the minimum in log n, and whenever we push, maybe a space of 5 got 2 of its slots used, and it became a 3. Then we can push in this heap in log n, right? And so at the end of the day, we'll have 10 heaps. And actually, the heap of size 0 is useless, but we'll just keep it just for that. And whenever we want to move a group into one of the heaps, right? This one is of size 2, so we know we won't use the heap of size 0, we won't use the heap of sizes 1. We can use the heap of size 2, but we can also use the heap of size 3 or the heap of size 4, etc., right? We want the smallest index among all the heaps, the width of which is bigger than the size of the block, right? Here, for example, 99 doesn't have anything in 2, so we'll look at the heaps of size 3 and we'll pop and we'll get this one. But maybe there was a heap of size 4, maybe there was 4, maybe here there was 4 empty spaces before the 0, 0, so we would actually use the 4, right? So we would use the minimum of the smallest indices in there. So let's open up the code and try and make that work. Hopefully with the code it might be a bit easier to understand well. So the first thing we'll do is pass the input. So we'll just transform the input in a list of integers, right? So we'll have, instead of this string, we'll have a list of those integers, and then we want to transform it into something like this, right? So I'll call this disk map with dots. So this list can contain dots, so we'll say ints of strings, and it will be of size at most 10n, right? Which is still big of n, so that's okay. Initially is empty, current ID is 0, so this is just passing the data, sorry. We'll iterate through the string they gave us, right, which we converted in ints, and if it's odd, then it's a free space, so we just add dots. If disk map I is bigger than 0, right, if it's 0 free space we don't do anything, otherwise we'll just add disk map I dots and indentation as well. Otherwise it's a file we just want to do the same, except we don't add dots, we add card, and we increment card. Alright, so this is just passing, right? This should be fairly easy. Now, whilst we passing this, we want to create our 10 heaps, right? So I'll make a list of heaps. So in Python, heaps are represented as arrays. So we'll have one heap queue per size, and those are min heaps in Python by default. And so in heaps free space I, we store the indices where there is I dots in a row. Right, so for example, if I'm looking at heaps free space 3, I'll get 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 3 elements in my heap. And so that means every time we create those dots, we also want to push heaps free space. So the size of the free space will be disk map I, and we add the index, the starting index, which is not I, sorry, which is the length of disk map with dots before we add the dots, right? Initially, maybe let's take this input, so 7, 1. We have 7, 7. Sorry, we have a block of size 7, 4, 5, 6, 7, and then we have one dot, right? So before we add the dot, the length is 0, 1, 2, 3, 4, 5, 6, 7. The length is 7, and it also corresponds to 0, 1, 2, 3, 4, 5, 6, 7. The first free space is the 7th index, right? So that's how it works. And we don't want to do append, right? Append would work if we actually had a list of lists, but we want to use a heap, right? And we want to, every time we push, the heap stays such that we can pop and look at the minimum elements fast. So we do heap q.heap push, my heap, and what I want to push into it. So that's how we pass our input, and we can check with the example that we actually get heaps of size 0 is empty, right? Because there's no free space of size 0. We said we wouldn't really care about this one. And then size 1, size 2, size 3. So we have 5 empty spaces of size 1, which is coherent. We have 1, 2, 3, 4, 5, right? And this respects the heap property, which is I is smaller than 2 times I and 2 times I plus 1. Sorry, 2 times I plus 1 and 2 times I plus 2. You can find this just by saying heap q python, and yeah, this property is satisfied. But that module just takes care of everything for you, so you don't even have to care about how it works. It's good to know how it works, but it's not compulsory. And then we'll do what we said, right? We will deal with all the files from the end. So we'll start at the last index of this, and first thing we have to see how wide is each file, right? So we would want to know that the file ID is 9 and the width is 2. Obviously, if so, while I is bigger than 0, if it's a dot, then we just continue, just I minus equal 1. Otherwise, we want to know what is the file ID, which is what's at index I, and we want the file width. So what to do that, we'll initialize this at 0, and we'll go to the left. So I'm here, and I'll go to left until it's not a 9, right? So if I'm here, I have to go twice to the left until it's not a 9, so it will be width 2. So that's how it works. We'll get a second while loop, file ID, file width plus equal 1, I minus equal 1. So you might think there's 2 nested loops, so it's n squared. It's actually not, because the 2 nested loops are working on the same index, and I can at most change its value n times, right? Or like 10n times. This is actually 10 times n, but it's bigger than. So now we have the file width, we have the file ID, and we want to swap with the leftmost free space that has the same width or bigger width. So we'll say small index is infinity initially, and we'll say the best width is initially something random, and maybe we'll find a free space of size 4 at index 10 and a free space of size 5 at index 7, right? And we want to say, well, I will use the free space of size 5, even though my width is 4, right? Because we want the leftmost. So we'll just iterate from file width to 10 non-included. If the heap q is not empty, the heap is not empty, and if the smallest index is bigger than the minimum of this width, that means we have found a better smaller index. We have found a better smallest index. So that means we update this and we update the best width, so that at the end we remember which heap we should pop from. If smallest index is 10 to the power of 18, this means there is no free space on, so no swapping can be done, right? So the only thing we would do here is just continue. Right, this is the case, for example, for 8888, right, is size 4. The only free spaces are of size 1 or size 3, so we don't want to do anything. So if that's not the case, we also have to check if the smallest index is smaller than I, right? Why do we want to do that? Because maybe let's say we want to swap 4 here, and this is not free, right? There is some free space here, but because it's on the right of 4, you don't want to swap, right? In this case, there's free space here, but I'm just saying if there was no free space here, if there was something like right, if we had something like this, and ignore the rest, we don't want to bring 4 here. Right, even though there's free space here, because it's on the right of 4, we don't want to do anything, right? So I modify the example just to show. Let me refresh. And so if smallest index is smaller than I, that means we're good to go. So if it's bigger than I, we would swap to the right, which we don't want to. So we'll just continue again. And now we know we want to. We know we can swap, so we'll just pop heapq.heap pop heaps free space best width, because we want to remove that free space. We want to replace the elements, and then we want to push if we need to push, right? Then we want to push heaps free space best width minus far width. Because let's say we have a space of 6, we put a file of size 2, we want to push in the heaps of size 2 that we have a new location, and we want to push in small index plus far width, right? Because if I'm using, this is size 5, sorry, if I'm using 2 elements, then my new starting index is this, is my former starting index plus 2 if it's size 2. So that's just the logic here, and we want to change the for chain range far width. We want to say disk map with dots smallest index plus j equals file ID, and we also want to say disk map with dots I plus 1 plus j equals dot, right? So this is just basically removing the 2 9s here and adding them here. And that should be it. We can run to see if I didn't make any mistake. Usually I make loads of mistakes, so we can see. Did make a mistake. Yes, we're not checking the list of heaps. If the list of heaps is empty, we're checking if the heap we're looking at is empty, right? So this should be this. And I didn't print anything. Yeah, sorry, I did not finish. At the end, we need to output the file ID times the index, right? So we want to do something like answer 0 for I in range disk map dots length of this plus equal I times disk map dot height. If that's right, this is big O of n as well, so we're happy, and this is big O of n log n because we do n iteration within the loop, and in each iteration the worst thing we do is a log n operation, right? This is at most 10 times, this is at most 10 times, so this is fine. Doesn't change the complexity. So finally, did I make mistake? We got 2928. So there is a mistake. And yet the second mistake is if the ith element is dots. We should ignore it. So now we should be fine. 2858. 2858, and then we can check the official puzzle input. And we get the right answer, and then we can use my sort of special input that should make the big O of n squared crash, and hopefully it won't make crash our solution. And we can see in less than 100 milliseconds we get the answer. So we are pretty happy with that nlogn solution.